Hello, and thank you, Paul. Um, Thanks for the opportunity to present here at the Geological Society of Australia in Perth. Um, this is work that I've been doing with a colleague who lives over in Sydney area in the Southern Highlands, Titus Murray. This is a picture of him here getting ready to fly a drone to get a picture of some outcrops. So anyway, here we go. Today we're going to be talking about faults, and are the faults going to be barriers? Or perhaps instead of barriers, are they going to be conduits? Or might they be both? And what we've done here is show you a variety of a few different kinds of faults. We'll talk more about some of the features of faults and how we think some new constraints help us understand fluid flow around faults. So just some terminology at the beginning. I'll talk about fault style or architecture versus also fault anatomy. So just so we're clear on fault style and architecture, I'm not going to talk so much about this. It might be thought of as something like tectonic style. So are we talking about thin skin deformation? Are we talking about basement involved? Are we looking at things like balanced cross sections? And what sort of techniques are we looking at to determine tectonic style? That's always important. But when it comes to groundwater flow, particularly along and through faults, we need to also consider what I'm going to call fault anatomy. And in the case of fault anatomy, often with a fault zone, three different main features are considered. The first one is, for example, slip surfaces. So these would be the frictional surfaces along which discrete amounts of sliding occur, typically with clear evidence of frictional wear and frictional features. Second major feature of active fault zones is a gouge or what's now called a fault core. So this is typically gouge cataclysite breccia. In some cases, it's re-cemented by fluid flow. The main feature of it is that it comes from the frictional wear. It's typically fine-grained, probably finer grained than most of the other rock. And then the third major feature is often called the damage zone. So this is the area that surrounds the fault, typically maybe both sides, but not always. And this is an area where it's thought that in many cases the permeability for fluid flow is enhanced because you've got increased fracture density that comes from deformation around the fault zone. Now, a key conclusion that I'm going to talk about today is our suggestion that fault core zones in particular are paper thin. So I'm showing there a picture of an A4 sheet of paper. I can show you one here. So here's an A4 sheet of paper, typical kind of size sheet of paper. It turns out that the length of the paper is about, say, 300 millimeters, and the thickness is somewhere around 1/10 of a millimeter or less. And if you compare that ratio to the typical ratio of the thickness of a core zone to the size of a fault, it turns out those are approximately the same. The picture at the bottom is from a fault zone in Miri, Airport Road in Miri in Malaysia. I'll talk about that in a little more detail later on. Now, the other thing about fault core zones, despite being paper thin, they also have holes. So this picture at the bottom shows a blow up of an area, so the area just near the dark glasses. And if you look carefully, you can see that there's zero core thickness there. So it turns out the core zone is very thin, has an aspect ratio about like an A4 sheet of paper, but it also has a lot of holes in it. And we'll present some information from recent research that sort of backs that up later on. Okay, so I was saying this is a log-log displacement, log-log plot of thickness versus displacement. And because it's a log-log plot, it covers quite a range in ratio of the thickness to displacement. So from ratios of about 0.1 to about 0.001. So that's similar to the aspect ratio of that A4 sheet of paper. Because it's a log-log plot, however, it's impossible to show holes or areas with zero thickness. They can't really be plotted on this log-log plot. If you consider instead a linear relationship, so this is something that we focused on back in 1995, there's probably a maximum value and a minimum value, and in many cases the minimum value may be near zero. And I think this is something that is potentially critical when you're talking about fluid flow across faults, and also something that we've missed when we consider the scaling of fault zones and the scaling of core zones along faults. So there are many modern compilations that show this data, the same kind of data. This is from the book by Fossen, published in 2016. The two plots show the fault displacement versus the damage zone thickness. So that's the rock around the edges of the fault zone that's, say, fractured, possibly an enhanced fluid flow zone. And then the bottom diagram shows the fault core thickness versus displacement. So in this case, it shows about the same proportionality constant as the data that I showed earlier. Again, however, these are still log-log plots, and you can't show holes or zero values. So that's where we're going with the sort of the basics of the presentation. Those are some of the key conclusions that I want you to take away, namely this fact about the A4 paper, and then the fact that it probably has holes in it. So the rest of the presentation, I'm going to show some examples from fault outcrop studies, and then I'm going to discuss some key areas of importance for fault zones and fluid flow. And these are groundwater, fault seal and reservoirs in the oil and gas game, and then mineralization and faults. So in particular, gold mineralization along mid-crustal fault zones. There are case studies, and there'll be some conclusions at the end. So I'll start out with the part about the fault outcrop studies. I mentioned the Miri outcrop. This has been studied in detail by my co-author Titus, and the main person doing most of the work was Silvia Socio de Rosa for a PhD thesis, and she has published a paper recently in Journal of Structural Geology. Good reading. It's a great exposure to understand and have a good look at. So the unique things about it is a lot of good exposure along strike that shows effectively the same throw in the stratigraphy because it's a normal fault. So we've got more than 70 meters of exposed strike length. There's lots of distinct holes where the core zone is not absent, and these are greater than, say, a meter and a square meter. There's numerous regions of very thin fault rock, and there are areas where there's lots of sand gouge as well as more clay-rich gouge material. So I want to just mention the possibility of a bias. So I say a Euclidean bias. So we're all, as geologists, we're all familiar with Euclidean geometry because we had to do calculus in school, whether that was university or high school or whatever. More recently, we've got fractal geometry. So Mandelbrot, the father of fractal geometry, shown here. So fault zones present characters that are both Euclidean and fractal. And so I think if we don't realize the difference, we can maybe be biased towards mostly going for Euclidean style of faulting and Euclidean styles of understanding for fault zones. And I think both are important. So this is the key thing that I think we've got to understand when it comes to holes along fault core zones. So fault nucleation and growth mechanisms influence the geometry of that core zone and the fine-grained materials. So the idea here is that as a fault develops, linkup or capture of smaller faults or flaws adds complexity and roughness. So the diagram shows maybe some fractures, small faults, and as they link up, you get things happening like relay ramps, and other complexities that as the fault grows and becomes more mature, you end up with in the plan view there some roughness or irregularities, and then in the dip view along strike you get a smoother situation. But the main thing is that there'll be a lot of complexity that comes from the initial geometry of where the starting fractures and faults are. And as the fault continues to grow, of course, this process goes on, linking together other faults of similar size or smaller or larger. So now what I'm going to do is show a few admittedly crude animations with only 3 pictures in each one. But the first one is, say we thought about faults as purely a Euclidean kind of thing, then we would expect that the core zone or the gouge would grow linearly in thickness and be pretty monotonic and simple and continuous. So in this case, I'm going to show the development of fault going sort of straight across the page from right to left. So next picture would be after some displacement. You can see that there's more fracturing and so on going on, but there is a now fairly continuous core zone or gouge zone. And with more displacement, maybe that you would expect that thing to just get thicker and thicker as time passes. And then various models of how these things work in terms of fluid flow make this assumption that you've got a fairly continuous gouge layer or fine-grained material that that grows in thickness and is comprised dominantly of the material along the sides, the wall rock from the fault that's been reduced in grain size. Now, if in contrast we consider something with fractal and self-similar roughness, so same thing, but let's say that we're going to focus more on the irregularities that get incorporated as that block diagram that I showed earlier. So if we then sort of start slipping, well, maybe the core zone, the gouge and breccia that forms is not continuous, and that as time passes, what you have is areas of fairly thick gouge and fine-grained material, and then you also have holes where it's essentially the undeformed wall rock on the two sides in direct contact. So that's a that's a mechanism or an understanding that I think I can contribute to the debate. Basically, how does this happen? Why do you have holes? Now, if we go and look at the Miri example from Silvia Socioderosa's paper, here's one of the key diagrams. The plot at the top shows the fault core thickness on the vertical axis versus strike length or distance along strike on the horizontal axis. And Silvia has done a great job at characterizing the outcrops in general. So here's some examples. Very, very good photography cases, and then very good mapping sort of on the 1 meter and less sort of scale. Very good exposures as well. So she's been able to develop a clear delineation of when the fault zone is covered and when it's available for direct observation. And what you can see in the plot is that there's frequent locations of zero or near zero core thickness, which is what led Titus and I, and Sylvia for that matter, to say, look, these faults have holes in the core zone or in the fine-grained gouge material. So the other thing that she's been able to do is do a proper geostatistical correlation diagram. So for this fault zone, observations seem to be well correlated at distances less than 2 to 3 meters. So if you go up to the fault in a particular spot, look at the thickness of the core zone, and then compare it to other places along the way, things look highly correlated at distances less than that, and at distances greater than that, not so correlated at all. So if you go more than 2 to 3 meters along the fault zone, what you saw earlier probably doesn't apply, and the conditions may be different. So you may have different type and style of fault rock. You may have different thicknesses. You may go from a thickness of 10 to 20 centimeters down to a thickness of 0. So that in a sense is what really has led Titus and I to say, all right, think of that fault zone as an A4 sheet of paper. But it's probably really important to consider that there's going to be some holes, and the character and distribution and sort of the size of those holes, I think, is an area of active research. It may scale with the size of the fault. We don't really know, but we do know that places where you can see a fault like in Miri, and where you can get really good exposure, continuous, that you do have lots of holes. So take that away, and we'll think about how that contributes to our discussions as we go on from here. Okay, so now the next part of the talk is where I talk about the application areas. I'll start out with groundwater. So this has been an exciting area for Titus and I to work in recently. I myself have been in minerals and hazards and then oil and gas for quite a while, and this is the first time I've done much work in groundwater, but this is actually fault surfaces, fault character, and groundwater in particular, not general groundwater sort of study. So one thing we've discovered is when you're doing a resource project in particular, there's often an environmental impact statement or environmental impact study that's required. And in many cases, particularly in Australia, it's all about groundwater. So they often talk about assets and developments, as shown in the first line there. Assets are typically a groundwater asset. So that could be a groundwater dependent ecosystem. It could be a bore field. It could be a wetlands, a lake, or a river. Any place that the water is used or part of a natural system is in some ways referred to as an asset. And then development could be anything that we're doing that changes the groundwater system. So it could be an underground excavation, it could be an open pit, it could be a coal seam gas project, any number of things. So one thing that wasn't obvious to us at the beginning, but has become really clear, is that actual risk assessment for groundwater needs to assess both the current day or the pre-development system and then the post-development system. And then of course you're not going to be able to make direct measurements on the post-development system, so you need to infer it. So because you need to assess the current day system, a critical thing to realize is that different study areas can result in different risks. So for example, the third point I mentioned there, let's say in theory, if you had exactly the same geology and the same resource project, so the same kind of open pit or underground excavation in exactly the same geology, but it was located, say, in the Flinders Ranges in South Australia or in Kakadu in Northern Territory, you could come up with a completely different assessment of the risk because the precipitation and the groundwater system that's existing prior to development is so different. The next thing to consider is what they call causal pathways. And it's a little bit confusing. Causal pathways are commonly defined as a sequence of events. And in some cases, that involves a geometric pathway, as you would think of maybe a flow path for water along faults, for example. So then it's important for us to just mention briefly that groundwater flow and the interface between, say, structural geology or traditional geology and hydrogeology, particularly for faults, needs to consider fault-related flow that's governed by either Snow's law or Darcy's law. So Darcy's law covers flow through a continuous medium like a porous sandstone. Snow's law covers flow along fractures, and that's important particularly for fault damage zones. And then there's also flow within existing aquifers, so that's typically Darcy's law. Then finally, one thing that we need to do as we're working through all these problems is we need to figure out the length and cross-sectional area of the pathways where the water can flow. And then we need to know a lot about the characteristics. So what's the fracture density, or what's the permeability? What's the porosity? How much water can pass through these and how fast given a certain assumed pressure difference? Okay, so that's kind of the map of where we're going. I just want to say a few words about causal pathways. So as I said, formally, a causal pathway is defined as a logical chain of events, either planned or unplanned, that link resource development and potential impacts. So this diagram shows a lot of different features in the surface, and a lot of these are events or changes in the hydrological system. Many of them have to do with human-induced sort of things that are happening. So you can see tailings dams, you can see open pits, you can see underground excavations. What you don't see in the diagram, however, is much complicated geology. So there's some layers in the subsurface there, but there aren't any faults. So it comes to us to sort of figure out how to deal with that. So the definition of causal pathways seems to be short on geological constraints and particular examples, and it's very detailed in human-induced changes and figuring out, well, what's going on when it comes to events. So we mentioned that just so that you get a picture of how they do this kind of work and what you might face if you ever get involved in building or creating one of these environmental impact statements. So now what I'll do is mention sort of three key scenarios for faults in groundwater. And these are partly motivated by what's going on over in Eastern Australia, where Titus has done a lot of work. The other place that I know groundwater is very important in West Australia is up in the iron ore country. And we haven't worked up there a lot. We have done a little bit of work in the far north, looking at agriculture and groundwater up there. But in any case, the three scenarios. The first one, faults are not important. The second one is there's no regional aquitard or sort of an impermeable unit that serves to separate your asset from the resource development. And the third one is that there are many aquitards or potential things to separate your asset, your groundwater, and your development, but there are big faults that cause complicated pathways. And so that one is where you really begin to get into some serious work about characterizing and understanding the faults. So here's the situation where the faults are not important. We know there are no faults in the region, or the faults have displacement much less than the regional aquitard thickness. And in this case, what you need to concentrate on is fault statistics and an isopac map for your aquitard. So what you can see is we have a regional aquitard, sort of a shale, we have a bore field, and then we have some coal seam gas development happening down under the aquitard. And if it really is unfaulted like is shown there, it's a relatively low risk situation. A second one is where a second case is where there's no regional aquitard and faults definitely can enhance the fluid flow or create new pathways. What's happening basically is that the proposed development is in the same aquifer or the same geological unit as the asset. So we show here a wetland right down the street from a proposed open cut excavation, or just around the corner from a proposed underground excavation, and there's a fault, and so the fault can have enhanced fluid flow, for example, through the damage zone, and can provide a new pathway of significance. Then the third situation is where you've got many aquitards or faults causing complicated connections. So in this case, we have a surface lake, and it can drain down into an underground excavation by passing through what's labeled as Aquifer A. It can pass through the damage zone along that fault, can pass through the fault zone onto the other side, through the damage zone, and through Aquifer B and enter the excavation. So a complex flow path is possible. So in this case, you need to understand the whole network, and you need to model the new pathways or the potential pathways with a combination of Darcy and Snow's law of flow. So Snow's law for the fracture permeability, and Darcy's law for the flow through the porous media, which could be in the aquifers or in the fine-grained fault core. So now I'll go through each of those three scenarios and show you a quick case study. So the first one is the Narrabri gas project, which is proposed by Santos in northern New South Wales. And as far as I know, essentially approved at this point. It is incredibly political, however, so that makes it quite interesting and a little bit new for Titus and I to be involved in looking at it. We aren't formally working on this project, but we've had a few good looks because we're very curious. So we know there are no faults in the, as I said before, what we want to show in this case, what we think is going on, there's no faults in the region, essentially no faults, or the faults that are there are very small. And we think this is probably not a bad scenario, or a fairly accurate summary of what's going on at Narrabri. So here's the project situation. The project area is actually in a mix of farming and forestry reserve and parkland. It's a project area of around 1,000 square kilometers, maybe about 20 by 50 kilometers, and that's shown in the red area there. It has been drilled for gas and coal in the past. The gas and oil wells are somewhat deeper, like 1 to 2 kilometers deep. Lots of water bores, of course, because we're talking about an area where there's a lot of cotton farming. So the water is used extensively in farming. This is the cross section that's been produced as part of the environmental impact statement by Santos. Note the extreme vertical exaggeration. So we've got 150 kilometers right to left, and only 1,200 meters or 1.2 kilometers from the ground surface down to the bottom is shown there. So extreme vertical exaggeration. The main features are we've got the Great Artesian Basin Aquifer. So that's a big aquifer in that part of the world. Then there's the Narrabri Formation alluvial aquifer and all the water bores that are servicing the cotton fields. That's a very much more limited size aquifer. Those two aquifers are in direct contact with each other in some places, and in many cases it can be shown that the alluvial aquifer is recharged by flow from the Great Artesian Basin Aquifer. There is then the coal measures that are going to be exploited for, that are proposed anyway for exploitation of gas, are fairly deep and much older. So they are actually as old as Triassic, and they lie beneath a aquitard, two of them actually, the Napperby Shale, which has a mean thickness of about 140 some meters with a standard deviation of say 45 meters, something like that, and also the Digby Formation Shale, which has a mean thickness somewhat greater, again about a standard deviation of 46 meters. So two fairly substantial aquitards isolating the aquifers, or the surface assets, from the coal. So in theory, it looks like a fairly good isolation. What we're curious about is, are there really any faults, or what is this system really like? So the cross-section doesn't really show any faults, and then that was something that Titus and I are working on right now to come up with a better cross-section. What I can tell you is that the data we've got, the data that's available, that's publicly available, looks pretty good and seems to support that conclusion. There is a structure contour map which is constrained largely by 2D seismic, but also by fairly abundant hydrocarbon drilling, with drill holes going down to 1.5 kilometers, something like that. The vertical resolution in the seismic is probably 20 meters or better, so that the various image horizons are fairly easy to interpret, and it seems very unlikely that they would be hiding, that there would be faults that are hiding with more than say 50 meters vertical separation, and probably it would be very hard to put in faults that are even separations as big as 20 to 30 meters. So the picture at the right does show where some faults have been interpreted. They're quite small in character, however, not very big displacement. And because they really don't serve to totally offset or breach those aquifers, we're feeling like it's a fairly good situation in terms of isolation between the asset and the coal seam. So, as I said, we're studying this in more detail to make sense of the current EIS and some published papers about methane transport and origin. And we're going to produce a well-constrained cross-section that won't have so much vertical exaggeration, and then try to make sense out of where the faults are that have been mapped in the area, and where the actual test data is. So where they're using test data and monitoring to make their conclusions in the environmental impact statement. And as I said, this one's very political, so it's interesting to just see what we think is going on. So I'll now go on to the second case study, which is a situation where you've got an asset and development in the same aquifer, the same geologic unit. So this one is the Roma North Field. Cenex is the company proposing it, and it's in southern Queensland. So I showed earlier an example of scenario 2, basically the asset and the development in the same aquifer. This is an open pit development. The Cenex project is coal seam gas again, so it is subsurface. But the concept is the same. You're basically in the same aquifer geological unit for both the coal seam gas development and the groundwater assets. This is a picture of the Walloon coal measures, which is the asset they're going to drill for the coal seam gas. As you can see, it's a fairly fine-grained and somewhat monotonous mix of shales and coal. It's not a particularly good coal, so you probably wouldn't be interested in developing it just for, say, metalliferous or energy kind of coal use. But it may be a very good source of gas, hence the interest in drilling it for coal seam gas. The situation in the map on the left, the lease areas are in red. There's a few major faults coming through, and the question is, will those faults have any impact on surface groundwater assets or near surface groundwater assets? So it then comes down to a comparison of, well, what sort of damage zones along those faults would we expect to potentially be important? So the lease areas are shown on both the map on the right and the map on the left. The map on the right is shows the groundwater, the drainages and the topography in a sense. The main groundwater assets are shown in purple and brown. Purple are special areas of significance for groundwater dependent ecosystems. So these are where certain flora and animals may depend on the groundwater resources. And if those are drawn down or compromised in some way, there could be significant damage. And then there's also superficial water resources like lakes or particular rivers that are similarly valuable. So what you want to do is be able to make an estimate of how much risk is there from the coal seam gas development and the pressure changes that would be induced by that, and those groundwater assets. So here's another picture then of the cross section showing one of the major faults, the Walloon coal measures in dark gray. And then at the bottom, there's a stratigraphic section summary that they've produced that illustrates what's going on in this case in terms of the basic stratigraphy. So in this case, what you want to do then is figure out, well, where do you think there's going to be damage zones along the faults, and how much permeability enhancement or flow enhancement can occur along those, and what effect will it have on those key groundwater assets that I showed in the last slide. So a little bit different situation than the one that I mentioned before. So in this case, what you're going to need to concentrate on is, what are those faults like? What flow paths might they provide? How much fracturing is there around the faults? Over what size of an area? And what would that fracture permeability pathway look like? How thick? How many fractures per meter? What would the fracture character be? And how much fluid could you expect to flow along that? And then, of course, to finalize the risk assessment, you would need to come up with an estimate of how those rates that you calculate for the fault-related flow, how those compare to the natural system and what's going on in the natural system. So scenario 3 is the most complicated, perhaps. Multiple aquitards and faults provide connections. So this situation, there's not too many obvious case studies that we can share, but we can tell you that this does occur in Southeast Australia, particularly in some coal mining situations. And the key elements would look something like this schematic cross-section. You have a surface asset of some type, like a borehole, bore field or lake, and then the water can percolate downwards to an underground excavation through the aquifers, through fault damage zones, across fault core zones, and then through other aquifers. And in some cases, there's multiple crossings of faults, so the fluid can flow on one across the fault, then jump into another aquifer on the other side, flow down, and then jump across to another aquifer again. So in this case, you would need to model fairly complex flow paths and come up with estimates of how big those flows would be in comparison to the natural system. So that ends the discussion of groundwater. It's been interesting to Titus and I to be involved in that. So far, we're working on how you would approach these kind of developments, in particular when it comes to coal seam gas, because we are very active in the oil and gas arena. So what I'm going to do now is talk about a little bit more general topic, and that's conventional hydrocarbon traps and what's known as fault seal. So for those of you who aren't so familiar, often with hydrocarbon fault seal and in exploration, the project is generally about estimating the size and fill level of potential hydrocarbon traps. So a typical trap is an area where oil and gas can accumulate in a conventional, say, porous sandstone reservoir, or sometimes carbonates, sometimes fractured materials. In any case, there's typically a top seal and a lateral seal. The lateral seal can be a folded structure, a stratigraphic pinch-out, or a fault, and the top seal is typically an impermeable sedimentary unit, like a shale, sometimes like a salt or something like that. Here's some of the terminology. So the hydrocarbons shown in green, that's traditional for oil. The trap itself, we would say we have a crest elevation. We have an observed hydrocarbon water contact labeled HWC, And if we have fault control of the fill level, it might be as shown there, where the hydrocarbons rise up and then fill the top of the fold until they leak out across the fault to the right. If that fault is also a seal, then what might happen is it would fill to a deeper level where it would spill across the syncline area to the right and go up in through the reservoir off to the right. So that might be called the lowest closing contour, or the fill to spill level. So then, focusing in on this area around the fault in a little bit more detail, there are a couple of cross-fault flow mechanisms and seal mechanisms that are in common discussion and use in the industry. So we talk about, if we look at that area where the fault is sealing the hydrocarbons, in detail, it might look like what's shown below in the blow-up diagram. So we talk about primary juxtaposition seal, and this is where, say, you have a porous reservoir rock with some permeability that's juxtaposed across a fault against an impermeable unit, like a shale or the top seal material. That's termed primary juxtaposition seal because the seal occurs dominantly because of just juxtaposition of an impermeable material against the reservoir. The second area is labeled secondary juxtaposition plus membrane seal, because what happens here is the seal isn't because of the juxtaposition of the rock on the other side, it's because of the fine-grained material along the fault, hence membrane seal. So this is where fault core materials that we talked about earlier potentially become important. And then to estimate and play around with this, there's a multitude of algorithms and methods to estimate the efficiency and the character of these types of seals. So we're showing one of the algorithms in theory there. It's called the shale gouge ratio algorithm. So what is done is you estimate the composition and character of that fine-grained material by knowing something about the rock on either side, and then making an assumption about how that might control the composition of the fine-grained material. A lot of assumptions involved, and I guess implicit in the general assumption is that there are no holes in that material. So I did mention an important thing earlier. We think there's, in many cases, a problem with holes. So you don't just get a nice uniform thickness layer that's continuous in many of these situations. So we've recently published on this particular aspect, fault seals and membrane fault seals. Here's the reference. I'll put it in the final slide as well, so you can look at the references there. Basically, what we did in this study is we used a library of known hydrocarbon accumulations to investigate the seal character and effectiveness. So there are 6 to 8 actual case studies in our publication that are mentioned, and then there are a lot of other ones that are confidential in various other stages that we've used to make the inferences that I'll relate to you today. So typically, each one of these known hydrocarbon accumulations consists of a pack of pre-drill data that you can think of. Well, this is what you would have had before you actually drill a well. So you might have, say, 3D seismic, which constrains the trap geometry. So you can interpret where the faults and folds are. You can get an idea of where the crest and where the lowest closing contour or spill point would be. So that's geometric information. Then there's also stratigraphic information. So you might have an offset well that could be quite far away, or some knowledge about what kind of stratigraphy is there. So you'll get an idea of what sort of things are appearing as the different stratigraphic layers. So you take that information and then use the pre-drill information. And then we also need to make this study work, is we need also post-drill data. So we need confirmation that there really were hydrocarbons there. And we want to know something about where the hydrocarbon water contact, or HWC, is located. And that's what elevation is it located? Where is it? So the key conclusions that I'll try to convince you of are that, number one, juxtaposition is the main game. Fault membrane seal, or that secondary seal, is rarely required to explain the observations of the case studies that we've analyzed. A second conclusion is that there's almost always enough charge. We really can't see very many places where a trap is partly filled. So it does seem that when you've got a hydrocarbon system producing hydrocarbons, there's almost always enough. So traps are almost always either filled to a fault-related leak point or a structural spill point. A third main conclusion is we can't see a lot of evidence for geomechanical or fault reactivation control. So this has been a very popular idea, but it seems like really juxtaposition will explain almost all of the cases. So there are, for example, cases of known very active faults that are seismically active that still function as lateral seals for hydrocarbons, and there are cases where it's known that the hydrocarbons travel up faults, but when you're looking at sort of in the exploration realm, how do you explain the observed hydrocarbon water contacts? We can't really find any that seem to require that we use a geomechanical or fault reactivation control kind of model. So just going back then again, reviewing it again, our method in this study is we take our library of known hydrocarbon accumulations. For each case, we make a pre-drill prediction based on typical exploration data, and that means we come up with a juxtaposition hydrocarbon water leak point. We come up with a secondary or shale gouge ratio plus juxtaposition hydrocarbon water contact leak point, and then we compare those with the independent observations that are from drilling. So there's no calibration involved. We don't use the observed hydrocarbon water contact in the model prediction or in making the prediction at all. We just look for the pure geometry and convolve that with the stratigraphy to come up with an idea of what, why, and where the thing works. I'll just mention a key paper that we really like, published in 1989 by a fellow named Urban Allen. What's shown in the diagram there is a long section of a fault that's a lateral seal for a hydrocarbon deposit. And what he's done is he's shown the hanging wall and the footwall both on the long section. So the hanging wall material are the layers that are continuous, and behind them are shown the footwall material. And the reservoirs themselves are the closed polygons, and the area between the reservoirs is the seal. So what he was able to talk about was if you say charge the layer with the yellow accumulation with hydrocarbons, it can leak out across the fault at point X and then rise up until it gets to point Y, where it leaks back across the fault and fills up that reservoir in the footwall, a different one than was the first one. Then what can happen is it can leak at point Z or Z and go up and continue percolating its way up through the network. So these fault profile diagrams have become known as Allen maps, and those of you that say do gold deposits and look at long sections of fault planes or shear zones and look at gold grade along them, you'll find some interesting parallels between what's now called Allen maps and those kinds of mining related diagrams. Interesting stuff, nothing particularly difficult. However, we're finding that far too often it seems that the basic geometry has been neglected, and this kind of constraint is lost in favor of other much more complicated mechanisms and types of complicated things that are complicated analyses that in some ways hide the basic geometry that you really do need to consider. So highly recommended paper. So then going back to just a quick review, and I'll run through one small case study to give you an idea how the method works. So typically we'll start with a good quality reflector. So this is a structure contour map of a good quality reflector showing high points that could be potential oil and gas accumulations. So we take the faults that are the most important ones. We can run a lot of different analyses and decide eventually, well, these are the faults we need to concentrate on. And then we digitize or collect the elevations of the hanging wall and footwall intersections of that horizon with the fault zone. And that gives us information like this. The top diagram shows the position of the footwall and including the elevation in sort of purple, and the position of the hanging wall in the light blue or cyan. From that, we can subtract one curve from the other and come up with the throw profile, which is shown in green in the bottom diagram. Then what happens is we approximate that with a second order polynomial, which enables the ongoing calculations to be performed. We then perform a Monte Carlo treatment of the fault geometry, and for that we describe each of the faults with parameters such as the length, maximum throw, symmetry, and that sort of thing. Each parameter in the fault description is described with a statistical distribution. So that enables us then to go ahead and do a Monte Carlo treatment, wherein we randomly select all of those from all of those variables and create an example or an instance of the fault geometry. We do that over and over again. In order to use the stratigraphy as well, we block the stratigraphy into basically three types of layers: reservoirs, seals, and thief zones. So reservoirs and seals are obvious. Seals are impermeable over geologic time. Reservoirs are permeable and capable of holding oil and gas, provided they're sealed on the top and on the sides. Thief zones are a little bit different in that they're permeable, but only over geologic time, but not sort of the shorter human scale. So if you have a thief zone and it allows the hydrocarbons to leak out very slowly, your trap can be essentially empty after a long period of time. So then the stratigraphy is defined using statistical distributions like the fault geometry. So we make an estimate of the stratigraphic thicknesses of the thief zones, seals, and reservoirs, and then we also make an error estimate of how likely those values are. And we also do that with the compositions. So we want a V-shale value for each of those layers in general. And it can be a summary one, rather simple as shown here, not like fully calculated, say, from log data like gamma ray. So then the stochastic trap analysis, or the Monte Carlo procedure, goes ahead. And we do that one fault block at a time. So each block that's bounded by faults on the sides. Each fault block can have a lot of faults, one or more, and each Monte Carlo simulation produces 10,000 Allen maps or fault profile diagrams. And these things are the things that are varied: the geometric features, the stratigraphic features, and we also consider the hydrocarbon specific gravity so that we can make a shale gouge ratio calculation. This is just a quick summary or illustration of how it works. So we start out with our stratigraphy and a reference horizon, which is the image surface in the structure contour map. And stacked reservoirs are constructed upwards and downwards from the reservoir surface. So we typically would start out with a footwall, or the block below the fault. So there's the reference horizon and the first reservoir. And then we would work upwards and downwards to construct the footwall geometry, or what's actually touching or intersecting the fault. So we would apply variable thicknesses of, say, the seal units and the thief zones and any reservoirs to create eventually a full footwall geometry of the reservoirs, the thief zones, and the seals. So that's just one Monte Carlo instance in this case. Then the next step for that particular Monte Carlo instance or realization is you add the hanging wall. You then look at where the juxtapositions of flow units are. So for the reservoir in the footwall, or the upthrown block, we could have leaks across to the other side of the fault across these juxtapositions. So for those juxtapositions, we calculate the elevations. We also calculate the shale gouge ratio, or the probable effect of any membrane seals, and then come up with an estimate of where the fault is actually going to leak. So then, since we've got 10,000 instances, we can do great geostatistics. So we can decide if there's multiple faults, for example, say fault A and fault B. We can get a percentage of when fault A controls the hydrocarbon water contact, a percentage of when fault B controls it, and a percentage of when the block might be filled to a structural spill point, or a non-fault related level. So we can then create distributions of the hydrocarbon water contact levels and also the column height. So that's what is the overall vertical column height of hydrocarbons. We can then compare the predictions to the post-drill or the independently observed hydrocarbon water contacts. So a great way to use a bit of geostatistics and the error analysis inherent in Monte Carlo simulations to get an idea of what the errors might be, how we might be uncertain, say, in understanding the stratigraphy or the fault geometry, and putting that all together to come up with a prediction. So here's a very quick run through of a case study. This is the Ling Gu field in the Malay Basin, which has been analyzed by a lot of people doing fault seal work. What we can look at is we can see an obvious crest. We can see an observed hydrocarbon water contact. That's the edge of the red area. So that's the typical color people would use for gas. So there's a level of the observed hydrocarbon water contact, and then there's a spill point. So the lowest closing contour or spill around this fault is there at minus 1425 meters in elevation. If we digitize the fault data, we come up with these fault profiles and the slip distributions for two faults. That's fault A and fault B on the east side and the west side. The other ones are minor faults, and if you do a lot of analyses, eventually you convince yourself that these ones are not anywhere near as important as the two on the end. We also then, of course, have to take a guess at what the stratigraphy is. So in this case, it looks like a fairly simple situation where you have a reservoir and then a shale top seal and base seal above and below. Nothing particularly complicated in this stratigraphy, but it works surprisingly well at coming up with a good prediction. So now what I'll show you is just some of the Allen maps or the fault plane profiles, P10, P50, and P90. So on all the diagrams you can see the crest of the structure, which might not be at the fault. So of course the crest of the structure, if you go away from the fault, could be higher. What you do see here is just where the footwall and the hanging wall reservoir materials touch the fault. So the footwall reservoir is shown in purple, the hanging wall reservoir is shown in light blue, and where they're both touching each other is shown in yellow. And in this case, the prediction based on the P10 Allen map, which is one of the 10,000 ones, is that the predicted hydrocarbon leak point would be very close to the independently observed hydrocarbon water contact, which is shown in red. The other two red lines, of course, are the crest and the fill to spill level. So in this case, the prediction seems to match fairly well the observed hydrocarbon water contact. If we look at the P50 map, the prediction isn't quite as good, and it looks like the prediction is a little bit too shallow or a little bit too conservative in terms of the amount of hydrocarbons that are actually held in the trap. And then the P90 prediction is even a little bit worse. So there the prediction is even more pessimistic. But it gives you an idea then of what kind of predictions could be made with a combination of the Monte Carlo simulation and a good geometry for the faults and a good understanding of the stratigraphy. What we can do then is come up with distributions. So we've got distributions of the predictions for both the primary juxtaposition and also then a secondary juxtaposition or a contribution from a membrane seal. And in this case, what happens is if you just talk about juxtaposition, you get a pretty good prediction, which is shown on the left. If you allow the shale gouge ratio or a fault gouge zone contribution or strengthening, what happens in this case is that sometimes that will seal and sometimes it won't. And that's the character of the shale gouge ratio algorithm. If it seals, then the prediction is that you'll fill to spill or fill to that structural spill point at about minus 1425. And if it doesn't, then you'll be very similar to the distribution that's on the left. So looking at the errors in these predictions, the primary juxtaposition error it gives us a 6-meter error. The prediction is a little bit conservative or a little bit shallow compared to the independently observed hydrocarbon water contact. If you compare that to the secondary juxtaposition and shale gouge ratio, or fault core zone enhanced prediction, what you can see is that there's a larger error, and there are many instances in the Monte Carlo simulations where the prediction is far too deep. So the error is up to 42 meters with a fairly large standard deviation. So it's pretty clear that the juxtaposition, primary juxtaposition alone, gives the best prediction in this particular case study. So we then, of course, have a lot of case studies. Here are the 6 case studies that are easy for us to use public domain data, so we're able to fully publish these ones and talk about what we've done in detail. And what you can see in the table on the left is a primary juxtaposition mean and standard deviation in terms of error, and that's error between the prediction and the independently observed hydrocarbon water contact. And on the right in the table, you've got the secondary juxtaposition plus a membrane seal or fault core seal contribution. And then on the right, we've got the primary juxtaposition error plotted in blue and the secondary juxtaposition plotted in red. And as you can see, we get a much better prediction from just using juxtaposition rather than using a combination of juxtaposition and a shale gouge ratio or membrane seal contribution. So in summary then, for oil and gas fault seal, juxtaposition alone gives the most accurate predictions, and most traps are fully filled with little evidence for insufficient charge. So it seems that charge risk may be systematically overestimated in the industry. So when you're in the industry trying to assess an exploration prospect, typically what you do is you estimate a variety of different potential risks. So there could be trap risk, there could be fault leakage risk, there could be charge risk, which is about how much charge is there enough. So an important then and sort of a little bit cheeky sort of summary that we have is based on this, if you're out there buying some oil and gas prospects, you probably want to buy those that look good on juxtaposition, and then if you want to on-sell them at a better price, you might push the membrane seal or the shale gouge ratio seal mechanism, because it is a little bit more optimistic. It shows taller hydrocarbon columns. In other words, larger amounts of hydrocarbons than are commonly predicted by the juxtaposition seal algorithm alone. So that's a quick summary of the oil and gas fault seal. And now what I'll do is carry on to a few fun pictures from faults and gold mineralization. So this one is a little bit less on the sort of conclusions and methods and details. I want to talk about seismic pumping and valving. I think it's a great story for gold deposits, and one I've had a lot of fun following over the years, partly because I'm a closet seismologist and I kind of enjoy seismology, and also because it seems like fault complexity and reactivation are potentially key concepts to understand. They're somewhat difficult to quantify and explore, but they seem to control where there's really good grade and where that sort of ounce per ton kind of gold grade can exist in mining situations. There are two big differences, of course, between gold and groundwater and hydrocarbons. And one is that the gold and minerals probably a higher temperature situation, sort of green schist to lower amphibolite grade, so much higher temperatures. And then probably also much more fluid, so a much greater volume of fluid. And the fluid moving around probably affects the system a lot more than it does, the geometry of the system a lot more than it does in oil and gas or groundwater. But that having been said, there's some interesting and fun bits of a story here. So I just want to mention a little bit about the geometry of faults to start out with. We all know that if we look down at map view on, say, a normal fault, it'll often have fairly large scale undulations or striations or what you could say, or entrance along the range fronts. So this is a typical basin and range province fault zone in the USA. And if you look down on it, it's got quite a rough or irregular sort of trace in map view. If you compare that to a strike-slip exposure from something like the San Andreas Fault or the Alpine Fault in New Zealand, and look down on those, the geometry is much flatter or straighter. So what is that all about? Well, it is about sort of the evolution of the fault zone and how fault zones are formed and what drives them to become straighter or flatter. So you can look at also normal faults and what some people would call corrugations along the normal faults, or even some people call them mullion structures. So show one here, which is from southern Malta, which is published and described in great detail by these guys in 2005. And also here's a normal fault in a gravel quarry in the Basin Range in USA in Oregon. So you can see in both cases sort of some undulations at fairly large scale. They're both exposures on the order of, say, 20 to 50 meters tall in quarries or along natural exposures that have to do with, well, along natural faults, natural exposures or quarries. So to just think about them a little bit, and these corrugations, I went out to the backyard and grabbed an old piece of roofing iron and put two pieces of it together and thought about, okay, well, if you slip one past the other, you can see what happens. It's quite possible for these corrugations to be quite happy with one another and slip along with normal fault movement and not cause a lot of problem or evolution of the geometry. What can happen, of course, though, is if you reactivate or move in a strike-slip sense, that then immediately these corrugations then are not so happy and they might open up. So I keep this in mind when I look at some of the gold mining faults that I've worked around and near and underground, and I think it's an interesting idea to consider. So this is a great example. I was very lucky to get to work on this one. It's a high-grade vein kind of quartz mine, much like what we would have here in Stowell in Victoria or perhaps Norseman. And we have discovered a few of these in recent days, but mostly these are what the old timers would have mined because they were looking for quartz veins and visible gold. So in this particular example, what you're looking at is a LiDAR image of the stoped surfaces. So you can see the horizontal drives at about 25 meters separation vertically. And what happens when they go and stope out the fault zone and the quartz veins along the fault zone is they want to know, well, how much rock has been removed. So they go in there with a 3D laser imaging system, and they image the walls of the stope on both sides. It's very dangerous to crawl around and look at these in detail, but the LiDAR image of the walls is available, and you can mosaic these together and come up with a picture for the whole mine or for a part of it. And what we can see in here is some very large-scale striations or corrugations in the fault surface. So these are bigger than any of the quarry exposures that I showed in the last couple of pictures. So we're talking, say, 200 vertical meters and a long strike, quite a bit, 200, 400. The mine itself goes for about 800 meters to 1.2 kilometers on strike, a long strike. So the geologic story and the structures themselves, it looks like these large-scale corrugations have ductile vein quartz or ductile-looking vein quartz, so sort of continuous, happy-looking shear zones that probably developed relatively slow strain rates and fairly high temperatures. In contrast, we then have a later strike-slip reactivation that looks like brittle and frictional striations that's a different sort of geometry. So we have an early oblique slip with the red arrows showing, maybe plunging 45 degrees, and then we have a late strike slip system that probably is related to gold mineralization. But interestingly, the gold variogram and the correlation is much stronger in the direction that plunges about 45 degrees. So interesting story, and is it about the complexity in the fault surface and how it evolves as it changes from, say, oblique slip to strike slip? Are the strike slip events, for example, seismic, whereas the early oblique ones are more of a ductile shear zone going on? So in this particular mine, there's great examples of laminated veins and fault complexity and the relationship between the laminated veins and visible gold. It turned out that when you went and did some detailed mapping, the areas where the vein is planar, flat, relatively well behaved, that's pretty boring in terms of the gold grades. And where there are complexities and irregularities, you tend to have the visible gold and the very high grade bonanza zones. So very interesting. It leads then to the question, can we constrain the size and character of these deposits by reference to seismology or some kind of structural geology? I think you can. It's probably difficult, but because we think we understand that mechanism fairly well, you probably can say something about the size of the mine, how far the fault surface will go at high grade, what kind of seismicity it might have had when it was active, and you can probably relate that to the various orientations of the corrugations and of the frictional sliding surfaces, and that sort of reactivation that occurred in sometime in the history. So that leads me then to the conclusions. I'm about done with the presentation. So just quickly, we want to say something about what can be proven and how you carry on science when it comes to the fault zones in complicated areas. So Titus and I probably want to make the point that in many cases we can't directly observe the subsurface, which leads to some difficulty. So positive proof of mechanisms is usually very difficult. And then for me anyway, the key thing I want to say is showing plausibility is not proof. So if you go and say, well, I think it looks reasonable that this fault, say in an oil and gas prospect, was reactivated due to, say, some kind of seismicity, and then it leaked. If you show that that's geologically reasonable or maybe tectonically reasonable, that doesn't prove that that mechanism actually operated. Likewise, if you say that we think this fault is sealing to hydrocarbons because we can see this in a particular spot and see that in another area, in many cases you're just saying that it's plausible, but you're not proving that a particular mechanism has been operating. So in some cases, or actually most cases, I think it's most responsible to just sort of enumerate the possibilities and then argue them up and down in likelihood. That would be the case in many cases, in many situations where we're talking about mineralization as well. It probably also is appropriate in groundwater. So rather than thinking of proving mechanisms, I think it's far more common and much more common in science to be able to disprove hypotheses or mechanisms or show that they are unlikely. So we say that, look, you're proposing a reasonable mechanism if you can also show that it could be disproved, or you can prove that it's wrong. And so if you then can't find a way to prove that, or are unsuccessful at proving it's wrong, then that sort of strengthens it. But in many cases, it is easier to show that something is not likely to have been a mechanism than to show that it actually was. So this is good procedure. It's good scientific progress, but it can be viewed as negative and pessimistic. So then, if you're in the publishing game, so say you're in a university situation and you need to publish stuff, negative results are, of course, a lot harder to publish because they're not novel, they're not new, they're not unusual. They're just sort of, oh, we tried, we looked, but it didn't work. But that's very valuable in many cases. And when you have a lot of those from a lot of different sources and a lot of different spots, when you're talking about something like groundwater or fault seal, that information can be very valuable. So the other sort of fault zone contributions and conclusions, hopefully I've convinced you that fault zones are thin and that fault core membranes have holes. So I mentioned, the A4 sheet of paper analogy. Think of the fault core as sort of dimension aspect ratio, something like an A4 sheet of paper. And remember, there's a very good chance that it can have holes in it. The flow paths across faults like this, of course, then are going to be very short. So across the fault, say through a hole or through the membrane itself, is going to be very short, but potentially large in area. So the area of the fault is quite large, and the length of the pathway through that fault material is quite short. And that's important in your hydrological simulations or simulations of fluid flow. Now, in contrast, pathways along or parallel to faults, where you're going through fractures and damage zones, are much longer and narrower. So that's important as well. When it comes to groundwater, the risk can only be assessed holistically. In other words, you must characterize both the pre- and post-development hydrology, and for post-development situations, you need to be well informed by estimates and constrain the estimates. So a complicated kind of thing. And remember that story about if you had the same geology in a very wet place like Kakadu as you had in a place like the Flinders Ranges where it's very dry, it's very likely that the difference in the initial hydrologic system would cause you to end up with a very different risk assessment for the same development and exactly the same geology if it were to occur in the two areas. The summary and conclusions for oil and gas is that fault membrane seals or fault core seals are not required to explain most oil and gas accumulations, and that juxtaposition only, no membrane or no fault core contribution seems to provide the best estimates and the best predictions. So there are a lot of other concerns and a lot of other activities going on where we're talking now about fault seal, leakage along faults that are of great interest to the public. So I'll mention two, CO2 sequestration and then repositories for toxic waste or nuclear materials, for example. Now, these are highly regulated areas and an area where the public deserves to know what the uncertainties are. So as geoscientists, we want to be a little bit more transparent, a little bit more clear, and a little bit better at educating people about what the risks in these types of projects are. Titus and I have been making a call for some time to make a lot more data available so that we can work through these examples and verify the work of others in detail, particularly as we go into problems that are about CO2 or waste repositories. Okay, that's pretty much the presentation as I had planned. Thank you very much for taking the time to come along and listen, and we're open for questions. Please get in touch. I'll add the last slide, which has some of the key references that I've mentioned in the presentation. Thanks.